Welcome to the 8th Porous Media Tea Time Talks. With these webinars, we want to give junior researchers working on porous media the chance to present their work to the scientific community. This is meant to be complementary to geoscience and geoenergy webinars that you can find in our featured channels. I am Mohamed Nouraipur from University of Oslo. I am here with my co-organizers, Tom Bultgrace from Ghent University, Maya Ruker from Imperial College, Catherine Spurin from Imperial College, and in Esprit by Marcel Mourau from University of Oslo and Kamal Singh from Heriot-Watt University, who unfortunately couldn't join us today. With that, I would like to hand over to Tom and Maya, who will be chairing today's session.
Hello, our first speaker today will be Mamta Jotkar. After finishing her PhD in fluid mechanics from TIFR, India, she has held postdoctoral positions in Rio de Janeiro and in Brussels, and she is currently a Marie Curie Fellow at UPM in Madrid. Today, she will be presenting her work with Professor Anne de Witt from University Libre de Bruxelles, where they numerically studied reactive convective dissolution in the context of carbon capture and sequestration techniques. If you have any questions during Mamta's talk, please feel free to post them via the comments section. And with that, I'd like to hand over to Mamta.
Good morning, everyone. First of all, I would like to thank the organizers for inviting me to present my work on this platform. I will be talking about differential diffusivity effects in reactive convective dissolution. This work was conducted at ULB in collaboration with Laurence Rangy and Professor Anne de Witt. It will soon be appearing in Physical Review Fluids. As we all know, carbon dioxide capture and sequestration has been proposed to be a promising technology for mitigating greenhouse gas emissions. This involves capturing CO2 at production sites and injecting it into deep saline aquifers for its long-term isolated storage. In this context, it is crucial to improve the safety and efficiency of the process, and this is the main motivation to my work. When CO2 is injected in an aquifer, it rises above the host fluid, which is typically brine, until it encounters a cap rock. This is an impermeable porous matrix. CO2 or phase A then lies on top of the host phase. The two phases are partially miscible and separated by an interface. CO2 then begins to dissolve in the host phase, and the CO2-rich brine is denser than the resident brine. This gives rise to a buoyantly unstable stratification, and eventually a convective instability sets in. This is seen in the form of dense fingers that sink towards the bottom. This convective motion is favorable to the sequestration process since it improves the mixing between the phases and accelerates the dissolution of CO2 in the host phase. The dissolution flux is given as a gradient of A integrated over the length, and this is shown here. At initial times, flux follows a diffusive trend shown by this dashed curve. When the convective instability sets in, it departs from this limit and eventually settles into a higher asymptotic one. This asymptotic flux gives us a prediction of the amount of CO2 that can be dissolved in a given aquifer. The onset time for convection is referred to as T0. Both these quantities are important and help us predict the efficiency of a given system. Now, in the recent years, it has been shown that chemical reactions have a significant impact on the convective dynamics, and it is possible to enhance the dissolution rates with respect to the non-reactive one. Additionally, all the species involved in the reaction can diffuse at different rates and alter the dynamics. So our objective here is to identify the optimal chemical composition that would give rise to enhanced dissolution rates and to understand the differential diffusivity effects in the nonlinear dynamics. We do this numerically. We consider a homogeneous isotropic porous medium where phase A or CO2 enters through the interface at Z equals 0 into the host phase that initially contains the reactant B. A upon dissolution gives rise to an unstable density stratification and then reacts with B to give C via an A plus B gives C type of a reaction. All these species diffuse at different rates and contribute to the density of the host phase. For the simulations, we have used Yale software, which is a finite volume-based code developed in France. And in particular, we use the Darcy solver, which was developed at ULB. So the reaction diffusion convection equations for the solutal concentration of A, B, and C are given here in the dimensionless form, where delta B and delta C are the diffusivities. These equations are then complemented by the Darcy equation for an incompressible flow in a porous medium and a linear equation of state for the density, where Ra, Rb, and Rc are the Rayleigh numbers of these species and they determine the density contribution of the species. So the important parameters for this presentation are highlighted here, the diffusivities and the Rayleigh numbers of B and C, while we maintain Ra as 1. These are the concentration profiles without convection for A, for B, and for C. The interface contains A. At the reaction front, C is produced by the reaction, and the bulk mainly comprises of B. I will show you shortly that when all the species diffuse at different rates, an additional convection zone appears below the reaction front, and this is distinct from the equally diffusive scenario. To understand the instabilities that lead to convection, let us first consider this isothermal system where the two phases are separated by a miscible interface. When the top phase is denser than the bottom one, it gives rise to the classical Rayleigh-Taylor instability, which typically looks like this and is similar to what is observed in CO2 sequestration. Now, in a stable density stratification, it is possible to trigger convection when the species diffuse at different rates. For example, when the bottom species is fast diffusing, it gives rise to double diffusive convection. In these experiments, salt at the bottom diffuses 3 times faster than sugar and gives rise to this thin, long fingering pattern. This type of an instability is also known as salt fingering in oceanography, and it occurs when warm salty water lies on top of cold fresh water. Another type of an instability that can occur in stable density stratification is the diffusive layer convection. That is when the top fluid is fast diffusing, but the bottom one is slow. And this gives rise to a depletion zone above and an accumulation zone below. And typically these antenna-shaped structures are formed. So to sum up, in addition to the classical Rayleigh-Taylor instability, additional convection zone appears below the reaction front, and this is different from the equally diffusive scenario. We classify the density profiles here in the diffusivity ratio versus the Rayleigh number ratio. Most of the studies so far have assumed that the species diffuse at equal rates, and this is this horizontal line. For example, in this paper, we had shown that when all the species diffuse equally and the product C formed is denser than the reactant B, the density profiles are monotonically decreasing. This gives rise to very strong convective motion. On the other hand, in this region, when the product C is less dense than the reactant B, the density profiles contain a local minimum. This local minimum inhibits the progression of the fingers, and the fingers remain stuck close to the interface up to very large time. So the overall convective motion is weak. Now, when the species diffuse differently, it's an entirely different story. For example, in these regions where B diffuses faster than C, the density profiles contain a local minimum below the reaction front. And this promotes a double diffusive convection that couples with the Rayleigh-Taylor instability. In this representative case, where the product C is less dense than the B, I recall that in the equally diffusive scenario, the fingers would remain stuck close to the interface up to very large time. But when B diffuses faster than C, the density profiles contain a local minimum below the reaction front. B from the bulk is easily available for consumption at the reaction front, and this has an overall destabilizing effect. In the absence of double diffusive convection, the fingers would remain stuck close to the interface. Now, in these regions where B diffuses slower than C, the density profiles contain a local minimum at the reaction front, followed by a local maximum below it. And this promotes a diffusive layer convection below the reaction front that couples with the Rayleigh-Taylor instability. In this representative case, the density profile looks like this. So at the reaction front, C is produced, which diffuses fast towards the bulk, but B from the bulk is low. And this gives rise to diffusive layer convection that couples with the Rayleigh-Taylor instability. These two zones of convections are formed, and the interface between them remains flat in the course of time. The antenna-shaped structure of the diffusive layer convection can be seen here. So in conclusion, chemical reactions have a strong impact on the convective dynamics. And when all the species diffuse at different rates, it gives rise to an additional convection zone below the reaction front. I did not get into the quantitative results here, but we have shown that up to an order of magnitude decrease in the onset time can be achieved with the help of double diffusive convection. That is when B diffuses faster than C. And finally, the efficiency of the sequestration process depends significantly on the chemical composition of the host aquifer. I would like to thank ULB Foundation and FNRS for the financial support, and thank you all for your attention. This is my group in Brussels on a sunny day. To that, I will take any questions you may have.
Thank you very much, Mamta, for the very nice presentation. The presentation is now open for questions. Please feel free to post any questions in the comment section below. We will read it out so that Mamta can answer it. In the meantime, I actually have already a first one. Mm-hmm. So you say that the efficiency of CO2 sequestration depends very much on the chemical composition. So which are the most favorable conditions?
Yeah, so for example, we have to analyze the chemical composition of an aquifer while selecting a storage site and what are the type of reactions we can exploit and how we can enhance convection. So my point is that the chemical composition of the aquifer would be an important criteria in selecting the storage site.
Mm-hmm. Okay. So which storage site would you look for? So what characteristics should the storage have?
Yeah, this is a good question.
Just a testing.
Sorry?
You just would need to test the chemical composition to see whether.
That's right. Right. For example, in lab setup, there was a paper on Helishaw setup experiments conducted on a Helishaw setup, where they had used alkaline hydroxides that diffuse at different rates, and this shows very strong convective motion. But okay, it will be independent to every scenario.
I see.
I also have a question, actually. I assume the simulations you showed were done on homogeneous sort of permeabilities. Do you have any idea what will happen if if heterogeneity enters into the picture? Do you think the differences between the different behaviors will be strengthened? Or
well, of course, there will be an effect of heterogeneity, but to get a first approximation of the efficiency or the dissolution rates homogeneous, assuming that the system is homogeneous, is already saying something about the system. And I mean, of course, when you have heterogeneity, you will have additional effects, but yeah, I don't know. That is something to look at.
Okay, thank you very much. I do not see any questions from the audience. However, if you still have some, please feel free to type it. I'm certain that Mamta can reply to them later again. I would suggest to switch now to the next speaker, Ying Wang. He just graduated his PhD this month and is now continuing his research on machine learning applications in 3D digital rock analysis and efficiency computational methods in fluid dynamics. His work focuses on integrating deep learning into digital rock workflows and implementing efficiency flow simulations methods to that allow large-scale supercomputing class direct numerical simulation to be performed on workstations. So, Ying, the floor is yours.
All right. Yeah, great. Good afternoon, good morning, or good evening to wherever you guys are. It's nighttime here in Australia. So since I have 10 minutes, I'll talk about the efficient methods and some machine learning methods in pore scale flow. Obviously, in digital rock analysis, you have your imaging section and your modeling section. And today I'll focus on the modeling section. So let's see. Okay. Very briefly, I'll introduce that if you're talking about digital rock imaging and modeling, then from the imaging standpoint, there are limitations with regards to the resolution in the field of view that your hardware can achieve. And of course, during the segmentation process, there are numerous biases that can occur depending on what technique you use and whoever's using it. So there are a number of new techniques that aim to sort of surpass these limitations, but also from the modeling standpoint, today we'll focus on that. So if you're talking about pore scale modeling, then you have your direct methods, which is your Navier-Stokes equations, and solving them using finite methods or lattice-Boltzmann methods. And of course, you have your simplified models, which are the pore network models, the Laplace solver, and morphological methods coupled to pore network models, so on and so forth, for two-phase flow. Obviously, the direct simulation is extraordinarily intensive, and it scales. And over the last 10 years, digital rock images in 3D have ballooned way past what a direct simulation can kind of feasibly achieve with reasonable resources. So today we'll talk about deep learning and efficient methods in pore scale modeling. And the main thing I want to focus on is the idea that in pore scale flow and in pore scale modeling, what we care about a lot is the absolute permeability and the relative permeability. And something very specific about the absolute permeability and the relative permeability is that they're steady state. And at the same time, we also care about, depending on what transport phenomena that you're modeling, aside from just the number itself, K and KR, maybe you're also interested in the velocity field itself and the phase distributions for solute transport, wettability analysis, so on and so forth. So with that in mind, using the most direct methods available, are there ways of accelerating the computation of these steady state parameters and these particular velocity fields and phase distributions? So one way that you can do this is to use a Laplace solver, and this slide here is has a bit of information here to describe a technique where you solve the Laplace partial differential equation using a domain decomposition scheme. And what this allows you to do is it will allow you to solve for the velocity field, an approximation of the velocity field, and the permeability of extremely large digital rock images with workstation grade resources. Here on the top right-hand side, you can see a sort of schematic of the way it works. It's relatively straightforward. For those well-versed in mathematics, it uses the alternating Schwartz algorithm. And so an example of what you can kind of do with this technique is with a standard workstation with about 16 to 24 CPU cores, you can solve for a domain of the size of 2,500 by 2,500 by 7,000, which is at least here in UNSW, roughly the size that you get out of our CT scanners, which I'm sure is very similar elsewhere in the world with other people's hardware as well. If you were to use lattice-Boltzmann or with GPU acceleration, you would, for this particular one, we used 2,000 GPUs to achieve a similar result. But realistically, with some modern advancements, 300 to 400 GPUs could also suffice. The idea, of course, being that 300 to 400 GPUs still requires you to, submit your job to a supercomputing cluster to kind of get these kinds of results out with this kind of size. So very briefly, that's one particular technique you could use. But really, I want to focus on what I call accelerated steady state solutions to steady state flow problems. So the one thing to note is that when you run direct simulation with Navier-Stokes or Lattice-Boltzmann, the number of time steps or the number of iterations to reach steady state is dependent on the complexity of your geometry, and it's really, really slow in really tight samples, or samples with low porosity or poor resolution. And at the same time, you need to use direct simulation if you want the underlying velocity fields for other phenomena, for analysis of other transport phenomena. If you're just interested in the permeability, of course, your Pore network model or your Laplace method will give you a pretty accurate result. The idea is, and the hypothesis is, that if you make a good guess on what the steady state solution is, you could probably get a pretty good speed up compared to just using a very uniform initialization. So in order to test this, we can make estimates using Pore network models, Laplace methods, or convolutional neural networks, which I'll get into now. If you use a convolutional neural network to predict steady state flow, there's a lot of research has been done on this actually I should not say a lot of research. There have been a few papers published by computer scientists here and there about solving Navier-Stokes equations in geometries that are relatively simple, so circles, triangles, so on and so forth. But what I found is that if you begin to increase the complexity of the geometry of the domain, your predictions get worse and worse, and to the point where these velocity fields get so bad that if you try to run solute transport on them just as they are, you get this kind of profile. You can clearly see that minor fluctuations in the predicted velocity field will ultimately result in rather large deviations in, for example, here, concentration profiles, because concentration profiles don't self-correct during the solution process. Any errors that occur due to the underlying velocity field are compounded as the simulation progresses. But at the same time, we should say that much like Pore network models and Laplace methods, if you care about the permeability, then you actually get pretty good results. This is just an example of some relatively low permeability samples, and you get an R-squared value very similar to what you might get in Pore network modeling, Laplace methods, or regression using CNN, just predicting the permeability instead of trying to predict the velocity field. But of course, much like I hypothesized, if you took your predicted velocity field and you inputted that into a Lattice-Boltzmann simulation, just as an example, you would get a pretty good speed up. So here's the orange. So this tracks the permeability over the simulation time, and the blue one is just your standard initialization, and the orange one here is your accelerated, or your initialization by putting a predictor into it. And it corrects itself within 100 to 1,000 LBM time steps. So this is a CNN approach to this particular type of acceleration. What about if you wanted to use a Pore network model or a Laplace solver, right? Here on the left-hand side is your typical Pore network model workflow. You go from your pore space to your distance transform to your extracted Pore network using, say, for example, the distance watershed segmentation. And then you get your pressure distribution, which is discretely mapped back onto the pore space. And then it's smoothed out using a few Gaussian kernels, about 20 passes, I believe. My colleague Arash was the one who worked on the Pore network fields. And of course, you have your Laplace method, which takes a distance transform and then calculates the Dmax, which is very similar to the maximum ball. And then with these two numbers, you can calculate a conductivity map, which emulates Poisson flow in cylinders. And you can solve the Laplace equation, which is grad dot k grad p equals to 0, right? And you get your velocity magnitude. These velocity fields and pressure fields from the Pore network and Laplace method are estimates, predictions. So first of all, just as part of the investigation, we can take a look at the kind of errors you might get just to begin. And you can see that the initial estimates, just using them as a predictor, you get, compared to Lattice-Boltzmann, poor network models and Laplace methods, here we use the PFVS method, do pretty well. They do pretty well. You get some error. You get errors start to show up in the low end and on the high end, but you do pretty well generally. I think anyone would say that this is totally acceptable as a way of estimating the permeability in pore structures for upscaling purposes. And this here is just a visualization of the kind of differences you get. Naturally, if you project a pore network model onto the pore space, you get a lot of discretization, which you can see here on the far left-hand side. The Laplace method is visually quite similar to the Lattice-Boltzmann result, and the difference maps here show something similar as well. But of course, estimating flow in pore space by using a cylindrical approximation, of course, causes error as well, which is reflected in this particular visualization. And so much like you can do with the predictions from CNNs, you can do the same here and use those predictions to initialize a Lattice-Boltzmann simulation. What you find, of course, is that your convergence is again very fast, very, very fast, and your permeability result, which you can see, and one of the reasons why is that your convergence criteria is no longer as strict as what is needed to sort of predict the permeability from this yellow line. By setting a convergence criteria of 0.1 instead of 10 to the minus 5, you can see that even so, you get pretty much a perfect correlation here with the LBM results at a convergence rate of 10 to the minus 5. And if you take a look at the kind of time required, here for this particular data set of 100 samples of 256 cubed with a permeability that ranges from 0.7 millidarcies all the way up to 3.5 darcies. It's about 4 orders of magnitude. You can see that for the accelerated methods, PNM LBM and PFVS Laplace LBM, you can see that the simulation time is right on 2,000 time steps for pretty much all of the samples. The effect that I mentioned at the start of my presentation, where the simulation time to steady state depends on how tight your sample is quite visually apparent here. Your high permeability samples don't take too long, only 10,000 time steps. But your low permeability samples, as you can see here, take 200,000 or more. So you can get a 5 to 150 times speed up. Now, I'll also talk about multiphase methods here. So in multiphase methods, you can combine morphological estimates with direct flow simulation, and that's a pretty straightforward idea. Here's a visualization of how it works. When the system stabilizes, you can condense or remove non-wetting phase using a morphological approach, and any errors that occur during this morphological transformation will be, for the most part, handled by LBM itself. So, and you can continue this process, and what you find is that you can get snapshots of the steady state distribution quite quickly. And as a validation, there's a Guildhauser sandstone available on the Digital Rocks portal that Stephen Berg used and Farouk Alpak used for some relative permeability simulations. And I used the same one because it has some dynamic CT data as well. And you can see that using the light blue lines here and the light blue lines here match quite well with the LBM results, which are the dark blue lines here and the dark blue lines here. So I'd like to conclude by saying that when it comes to predicting physics with simplified models, you either have to live with the difference, you have to live with the loss in accuracy, or you could couple it with real simulation. And what what ends up happening is that you get a pretty decent speed up for it. And also at the same time, the underlying flow fields and the underlying phase fields become accessible as well. There are some future work that can be done with this. For example, you could use a CNN-based prediction for morphological transforms in two-phase flow, so on and so forth. And so that ends my presentation.
Thank you, Ying. We have a few comments or a few questions. First one is from Stefan Berg.
Oh, yeah.
He's asking if the two-phase simulation was drainage or imbibition.
So if you let that animation go for long enough, you'll see that it's both. That right now it's doing a drainage, as you can see, and if you give it a moment, and there's the imbibition. And for the validation, which is on this slide, the dark red line on this curve and the light blue line on this curve track the Euler characteristic versus the saturation, and the red line is the drainage, and the blue line is the imbibition. The dark red and the light blue compare against the light red and the dark blue in terms of the morphologically accelerated approach and the LBM only approach. The direct results from the CT scan, you can see, are these dark black dots that go up like this. And of course, when you do a morphological approximation, errors do show up. So you can get some aggressive snap off, for example. That's one thing that could very easily happen, and that's reflected here with the light blue line being higher than the dark blue line. This is during the imbibition process. These relative permeability curves come from an imbibition simulation.
Okay, and then we have a question from Catherine asking or saying that during her steady state experiments in multiphase flow, she observed intermittent flow pathways that meant that the relative permeabilities were fluctuating. Is that something that you could implement in the model?
Yeah, so the intermittency of flow path. So for example, say non-wetting phase might switch from one path to the other. I'm guessing that's what you mean. Yeah, I think that you would have to implement a more a smarter morphological transformation. In this particular implementation, the morphological transformation is very simple. It's just a shell that is removed or added to the non-wetting phase just as a function of the distance from the phase interface. The philosophy behind this approach is that LBM is supposed to sort of deal with everything else once you do that transformation. I guess for intermittent flow paths, a morphological approach would have to sort of be a bit more direct in the direction that it's going. Honestly, that's a bit difficult. That's a bit of a difficult thing to implement, and I think something like that, honestly, would be better off being done just using the LBM only method, in my opinion.
Yeah, I think so as well, as it might be mostly driven by the dynamics anyways.
Yeah.
That makes sense.
After all, this method is supposed to sort of emulate quasi-static, very low capillary number flow, which LBM and volume of fluid, these methods struggle to do in the first place due to spurious currents.
Okay, we have one more question here by Ace Saw, who is asking who's saying that imbibition would be a long-term process, and is asking if the model can consider this dynamic effect. So, I guess you kind of hinted towards that in the answer to your last question, right?
Yes, I mean, imbibition is a long-term process. I'm not exactly sure what that means. Perhaps in the sense that if you mean that imbibition takes a relatively long time to occur, during low capillary numbers, again, partially the reason why direct flow simulation fails to capture this in a reasonable time frame, then using a morphologically coupled approach would give you a quick estimate. Again, depending on how aggressive you morphologically transform and how much you rely on LBM to sort of fix your estimates, then you can get some aggressive snap-off effects. Yeah.
Okay. And then Mohammed is asking a question. Do you think these approaches can assist us in better handling of stability issues at high density ratios?
Maybe. Numerical stability issues at high density ratios, you would have to be very careful with that, because sometimes you run a simulation and it fails halfway. That's because suddenly there was a fast flow channel or something like that. Yeah, actually, to be honest, you could probably implement some sort of numerical algorithm or workflow where, as soon as something like that is detected, go back a few thousand time steps to some point where it was stable, and then push past it using a morphological method and hope that doesn't cause instability. But most of the time, but then again, one should also say that most of the time when you initialize a high density simulation, it fails on the spot. And there's not much you can do about that.
Okay, then I think that's it. Thanks again for your great presentation, Ying.
Yep, thank you.
And with that, we will close the session for today. The speakers next week are Anna Maria Eckel from Imperial College, who will be talking about solute mixing during density-driven convection, and Thomas Darwent from Nottingham Trent University, who's going to talk about fluid flow in complex porous media, spatial correlation, disorder, and deformation. So that's it for us. We are the Porous Media Tea Time Talks team. If you have any questions or comments on our sessions, feel free to email us at porousmediattt@gmail.com. You can also there ask us to inform you of upcoming sessions, and then we'll just send you an email every time we have a new session. So thank you again for watching, and thanks again, Mamta and Ying, for your great presentations, and we'll see you in 2 weeks.